Next topic is moving coil galvanometer. A galvanometer is a device which is used to detect the direction of flow of current in a circuit. The principle of galvanometer is a current carrying coil placed in a uniform magnetic field. It always experiences torque. So first we have to study the construction of a moving coil galvanometer. Here you just consider a coil. The coil is placed in a uniform magnetic field. Here it is a concave shaped magnet. This is the north pole and here it is the south pole. Field lines always moves from north to south direction. So inside the coil, a soft iron core is placed. This is the soft iron cylinder. Here the use of this soft iron core is, it is used to increase the strength of magnetic field as well as it is used to make the field radial. So inside the coil there is a spring. From the spring a pointer is attached. Here this is the spring. Here this is the pointer. And here a scale and mirror arrangement. Here this is a scale and mirror arrangement. Okay, this is the construction of a moving coil galvanometer. It consists of a coil. The coil is placed in a uniform magnetic field. There is a soft iron cylinder which is kept inside the coil. The use of this soft iron cylinder is to make the field radial as well as it is used to increase the strength of magnetic field. So next we have to study what is meant by radial field. Radial field means the plane of the coil which is always parallel to the direction of magnetic field. So first when we pass current through this coil, a torque acts on it. This torque which is said to be a deflecting torque. We already know the equation. Deflecting torque which is equal to A B I N sin theta. For maximum torque we have to take the value of sin theta is equal to 1. So A represents the area of the coil, B represents the magnetic field, I is the current flowing through the coil and N be the number of turns. So next at the same time, due to this torque, the coil turns through an angle phi and this is always equal to the restoring torque. The restoring torque acts on the coil which is taken as K into phi. Here K is said to be a constant. This is said to be restoring torque per unit twist. Or we can say this is a torsional constant. So at equilibrium point we have to say the deflecting torque which is always equal to the restoring torque. So that we can write K into phi which is always equal to A B I N. From this equation we can write phi is equal to A B N by K into I. If we consider this as a galvanometer constant, then we can write the deflection produced in the galvanometer which is directly proportional to the current. Next topic is current sensitivity. You know this equation. Phi is equal to A B I N by K. From this equation we can write phi by I which is equal to A B N by K. So current sensitive means deflection produced in the galvanometer per unit current. So 5 by I only represent current sensitivity. This current sensitivity depends on 4 factors. One is it depends on the area of the rectangular loop, and the second one is it depends on the strength of magnetic field, and the next one it depends on the number of turns of the loop, as well as it depends on the restoring torque per unit twist. So current sensitivity can be increased by increasing the area of cross section, increasing the strength of magnetic field, increasing the number of turns. At the same time, we have to decrease the restoring torque per unit twist. The unit of current sensitivity is, here the unit of phi, that is deflection, which is represented as radian, and current, the unit is ampere. Voltage sensitivity. So current sensitivity, you know this equation, phi by I, which is equal to NVA by K. By Ohm's law, you know the equation, I is equal to V by R. So that we can write phi into R by V, which is equal to NVA by K. From this equation, we can write phi by V, which is equal to NVA by R into K. So voltage sensitivity means deflection produced per unit voltage. This voltage sensitivity depends on 3 factors. The first one is strength of magnetic field, second one is area of cross section of the coil, and the next one is it depends on the restoring torque per unit twist. So to increase the voltage sensitivity, we have to increase the area of cross section, the strength of magnetic field, as well as we have to decrease the restoring torque per unit twist. So at the same time here, this factor, that is N by R, always remains constant. The reason is, when we increase the number of turns, the resistance of the conductor can be increases, so that N by R always remains constant. So next we have to write the unit of voltage sensitivity. Deflection, the unit is radian, and voltage, it is represented as volt. So radian per volt is the unit of voltage sensitivity.
If you found this video helpful, please like, share and subscribe to the channel. See you in next class.